Yeah, so thanks everyone for being here. Thanks for the organizers for inviting me to give this review talk. I should say it's a huge field, so I really have a very short period of time per topic, but I've done my best to try to cover as much as what people have been doing in this field. And to start, I should recall why, first of all, we are using AGN feedback. So the truth is that essentially every model struggles to reproduce the observational predictions of massive galaxies if AGN feedback is not included. And there's many ways in which models fail if AGN feedback is skipped. And I've listed here quite a few of them. So one is that galaxies are rather disky, too blue, too star forming. If you include AGN feedback, they become spheroidal, red, and quiescent. Star formation is too efficient in high mass halos. So this is what happens without AGN feedback. That's the red circle show you what happens when feedback is switched on. It's very difficult to quench massive galaxies that continue forming stars at a high rate. And then there's actually a long list of things that go wrong. So the chemical enrichment of star populations disagrees with data if AGN are excluded. You can reconcile it with data if you model that. X-ray luminosities are wrong. Lyman alpha nebulae are wrong if AGN is not included. And what's really striking about all these results is that they arrived at independently by different groups with very different models, very different subgrid prescriptions for star formation, supernovae, different code, different bugs, etc. So it's really, I would say, everyone really now includes a model for AGN feedback. And 10 years ago, there were actually only a handful of models available, many of which went back to 2005 when Tiziana Di Matteo and Volker Springel modeled quasar feedback through thermal energy injection in a way that is proportional to the estimated black hole accretion rate. And if you want to do a review of this topic, you're then confronted with what happened in the next 10 years, which is this. Okay. A lot of groups, a lot of different people have pushed AGN feedback models in lots of different directions. And what happens next is somewhat subjective. It reflects maybe the way I see these models. I think you can sort of recognize that there are different approaches. So some of them try to capture AGN phenomenology. One great example of this is the attempt of injecting bubbles directly in halos. That could be what happens when a jet interacts with halo gas. Other examples try to, for example, use observational constraints of mass loadings and momentum fluxes in large-scale outflows to motivate AGN models. Yet other approaches say, well, we cannot really resolve the underlying physics, so let's try to design a model which is efficient. We calibrate it against some observable with a tunable parameter, and then we test the predictions of this model, we compare it with observations, and judge the merits of this model in this way. So at least we may not know why feedback behaves in this way, for example, delayed cooling, but we may have an idea of how it should behave. And then we can think about what kind of model will give you this behavior. And more recently, there's been a push in the field to try to connect AGN feedback models to small scale physics, try to connect these a bit more closely. And I would say this is becoming increasingly the case in the field. There's lots of interesting work done on jets, interesting work done on winds, interesting done on radiation. Now, I will start with one of these fundamental models. It's also the one I spent the most time studying. And it goes back to actually where the review talk yesterday left, where we've seen that quasars and AGN are expected to launch fast winds from accretion disks. Now, at large scales, in a large-scale simulation, we cannot really hope to resolve that in any simulation that is performed over giga-year timescales. So what models start from, including analytic models, is the assumption that such a wind is in place. We don't know how it's launched. We just assumed, for example, that it has a speed of 0.1 c, a momentum flux of the order L over c, so the radiation field momentum flux. And we then analyze what such a wind would do as it interacts with the ambient gas. And there's been a huge amount of work done on understanding this analytically. It's basically the same as in the stellar winds problem that was studied in the 70s, but teleported to the AGN energetics. And what we know happens is that initially there will be a phase where the wind is dominated by kinetic energy. It will intercept a mass equal to its own mass, at which point the swept up ambient gas starts pushing into the wind, driving a strong reverse shock that converts most of the wind kinetic energy into thermal energy.
Stopping that away. All the way down there. Yes. You know what I'm talking about. I do. That away. That away.
Okay.
Sorry,
You go
could you go on
across
mute,
Broadway.
please?
Okay. Go to hit Broadway, take a left, then a right, and then it'll spin off of Canal. And then just go that way. You'll get to that bit. You'll get it.
So I don't know who's watching my talk from where. Okay, but I'm glad it's not something that I said. Anyway, all right. So if we conserve energy between what's injected and the large scales, we would actually arrive at the conclusion that the momentum imparted on ambient gas can exceed the momentum of the wind by large factors. So this comes out if you assume energy is fully conserved. Now, is that the case? So in the last 10 years, the consensus has been that yes, we do expect these shocked wind bubbles to conserve most of the energy. There's various reasons for that that have been uncovered in the papers. Plasma effects, the suppressed cooling rate of this shocked wind bubble, and also the fact that the cooling radius could be much smaller than the scale at which the kinetic energy is converted to thermal energy. So this means actually that including some kind of hot bubble around an AGN or around a quasar does not sound like such a silly thing to do to model quasar feedback, because that's what the you would predict. You'd predict there's some hot bubble there that doesn't cool. And in fact, if you run a simulation where you inject feedback through thermal energy injection, and you do this at sufficiently high resolution, you actually exactly recover the analytical energy-driven solutions. So this is a comparison between the analytic solution in a Handquist profile, and these circles are simulation results for continuous thermal energy injection. So there's nothing really, this model is actually quite good if the resolution is high. The problem is, in the kinds of simulations we run at large scales, our resolution is not sufficiently high. And most of the thermal energy that is injected is lost due to purely numerical cooling losses. So this plot here on the right shows an estimate and a comparison between how much thermal energy goes in. So this is as a function of redshift in different stellar mass spins, and these thin lines, which I cannot see from where I am, they tell you how much energy it actually survives cooling. And you can see that a lot of it can be lost due to purely numerical effects. Essentially, the gas cools down before the sound crossing time scale, before the wind or the hot bubble has time to really expand. So a lot of the field is driven by coming up with models that will correct for this cooling, numerical overcooling problem. And there's various approaches. So one of them would be that you no longer do continuous thermal energy injection. You instead store up this energy until it's sufficient to heat up the gas above some temperature at which the cooling time becomes long, and only then you unleash AGN feedback. Other cases, cooling is suppressed explicitly by really just preventing cooling for some period of time. In other cases, kinetic energy is added. As I've shown, this does not necessarily mean that you will overcome this problem, because this kinetic energy can be rapidly converted into thermal energy. But if this free expansion radius is large, you could, of course, offset cooling losses. And since I mentioned results from elasticity NG in the previous slide, I wanted to just mention another approach, which is to add more modes to the simulation. So if the quasar mode, for example, is not efficient, you could add a second mode that takes over at low accretion rates. And in the case of elasticity NG, for example, this is assumed to be kinetic, which means it's harder to cool. And what's also not so well appreciated is that actually the energy injected also is stored and released only when it becomes comparable to the binding energy of the halo. And moreover, there are various thresholds that are added by hand, essentially, to determine when a black hole is in the quasar mode or in the low accretion mode. And these thresholds, they introduce to purely out of numerical reasons to make sure the feedback becomes efficient when you need it. There's no real physical explanation. So I would summarize this as suppressing cooling probably to some extent recovers the expected behavior of a quasar outflow, but the ways in which we're doing this in models are not physical in many cases. They're mostly numerical, and we need to continue understanding how we can model that better and connect it more closely to a physical scenario. For people who are familiar with this analytical solution, maybe they're a bit confused about something I said, because you might have heard that cooling is actually one of the main explanations put forth to explain multi-phase structure in AGN outflows, and that's the case. But what I want to emphasize, it's not the cooling of the shocked wind, which is the one which is expanding adiabatically and driving the outflow. It's the cooling of the swept ambient medium that forms this multi-phase structure. And actually, the content that is lost, the thermal energy lost here, is quite small. It's only 20%. So if your quasar feedback model is cooling more than that, that may be a problem, right? Okay, I just wanted to show very briefly that people have been studying the cooling in these bubbles with a lot of detail. So here is an example from work by Alex Richings and Claude-André Fauché-Giguère, where a chemical network was used to follow cooling down to extremely low temperatures, where they actually resolve the formation of a molecular component in the shocked ambient wind. I also want to mention a potential problem for the entire picture of an energy-driven outflow, which is that many models assume, or they treat the expansion of an outflow in a homogeneous, spherically symmetric medium. In reality, this wind will interact with a clumpy multi-phase ISM. It will mix up, the wind fluid will mix with the cold clouds and will cool faster. And it's possible, if you have a large amount of mixing, that you actually lose the energy-driven character of these outflows. It's not clear whether they would become fully momentum-driven or whether there's a sort of partly radiative phase. What we seem to know also from analytical arguments is that you really need a lot of mixing for this to become a problem. But it's I would say, an open question, also one that will require modeling of transport processes like cosmic rays and MHD. I want to mention also what I think is, and I'm a little biased, but what I think is an interesting way to try to overcome the range of scales. So this is a model that we've come up with in a repo, where we take advantage of the irregular Voronoi mesh to generate this spherical boundary, which we place around each accreting black hole. So this is discretized with a Hillpix tessellation into a number of solid angle elements. And what you can do is try to connect this with small scale wind solutions, or for example, as predicted by GRMHD simulations, through appropriate choice of boundary conditions. And we've already tested this model, for example, in the case of an ultra-fast outflow, where we start the wind with 0.1 C, a momentum flux of L over C, and we're able to recover the analytic behavior and the multi-phase structure in a lot of detail. Of course, this can also be done in reverse for accretion. So here is a case where we've used this boundary to measure inflow rates across some of the solid angle elements. And we've also included the wind, which then escapes where the ram pressure of the inflow is not significant. Once you go into more realistic simulations, so not just homogeneous media, you can see what these spherical small-scale winds do and how they affect the galaxies. So it's clear that even if these winds are spherical, the large-scale outflow loses memory about the small-scale behavior of these winds. So it knows of the energy, but of course, the geometry, the speed, the temperature all change. And if you look at this video, you can actually also get an idea of what these winds do to the galaxies. So there is a clearing out of the galactic nucleus, which could suppress star formation and regulate black hole accretion. But what I think is actually more striking, but you just need to look at it for a lot longer, is what happens to the CGM. So if I go back to the beginning, the density was much higher than after a few cycles of this AGN outflow. So there are two things going on mainly. There is a short-term rapid suppression in star formation, which is not very strong because these outflows take paths of least resistance. And then there's a long-term suppression due to the prevention of accretion in these halos, essentially the ejection of the CGM. So I've talked now about winds, but there are other ways in which AGN may affect galaxies at large scales. And one of them is not discussed so often, is the possibility that radiation couples to dusty gas at kiloparsec scales directly. So this model has been proposed in the 90s to explain even the M sigma relation, for example. And the idea is the dust, which is assumed to be mixed and tightly hydrodynamically coupled to gas, absorbs the UV and optical photons. And as this happens, the dust grains receive a momentum kick in the radial direction. In the so-called single scattering regime, each photon does one collision at most because the photon will be destroyed after it's absorbed by the dust grain. But various people have mentioned that or highlighted that it is possible if the column density is particularly high and you have particularly dusty media, that even the infrared photons will be absorbed after they escape. And what happens then is that the infrared photons will undergo some kind of random walk until they leave the system. You can show that the force in this case can actually exceed L over C because there are multiple collisions and there is a preference for picking up a radial outward component. And in some configurations, spherical configurations for moderate optical depths, this actually goes roughly as the optical depth times L over C. What's not so clear is, do these conditions and the opacities in real galaxies actually come about? There's been work done to investigate this model. Here are radiation hydrodynamic simulations of high redshift quasars, where the single scattering and multi-scattering radiation pressure were investigated. What was found is that both of these channels are able to drive powerful outflows. But what's really interesting is that if you do not include the infrared trapping, the required luminosities are probably unrealistically high. But once you have a non-zero infrared opacity, and you have this effect that you're trapping the infrared photons and you're building up this additional pressure, you're able to drive large-scale outflows with these kinds of speeds at lower and more realistic luminosities. These models do make very optimistic assumptions about the dust properties, though. So they assume fixed dust-to-gas ratios. They neglect dust formation, dust and particulate dust destruction. More recent models with other codes, but also in radiation hydrodynamic simulations, have started to implement dust destruction growth in these large-scale simulations, finding that dust destruction, well, unsurprisingly, suppresses the strength of this mechanism. But I think that's still an open question, of course. Yeah. Now, even though radiation seems to, or radiation pressure on dust seems to be able to drive these strong outflows, it doesn't seem to be affecting the halo that efficiently. And this is because radiation pressure is efficient only if you have very high optical depths. And once this outflow goes into the halo and you are in this diffuse halo gas regime, the radiation couples much less efficiently. So if you compare, for example, the impact on the halo with what you get from an energy-driven wind, you can see that the energy-driven wind has a much stronger impact. And this is, of course, the energy-driven wind, this PDV work in the halo doesn't care if it's optically thin or optically thick. And this leads up to this question of the halo and how feedback modulates the content of the CGM in massive galaxies. I think this has been recognized in the last few years as a central aspect of quenching a massive galaxy. The massive galaxy is quenched if you are able to expel the CGM, essentially. It's seen in different models. This is for TNG, that's for EGO. So in this plot, for example, shows the CGM fraction, so the fraction of gas in the CGM as a function of black hole mass. This is that threshold where suddenly TNG initiates the strong kinetic feedback. And you can see that this galaxy has a much lower density, also has a much lower specific star formation rate than that galaxy that came from a simulation where kinetic feedback was excluded. That's one galaxy where the CGM continued gas rich. That's a simulation where the CGM mass was suppressed. That plot shows the same behavior in a different simulation. So it shows that the scatter in the CGM fraction is correlated with the scatter in the, or with the deviation of the black hole mass from the mean. So at a fixed halo mass, the systems with the higher black hole masses, which are the systems where more energy has been injected by AGN, are those galaxies where the CGM fraction is lowest. These also turn out to be the galaxies which have low star formation rates and are preferentially suppressed, whereas these galaxies stay gas-rich. So affecting the halo is important to connect to what I said earlier. If radiation pressure has a weaker effect on the halo, this is another argument for this energy-driven outflow phase. You really have to conserve the energy and couple that to the halo. Now to jump to something completely different, into a completely different regime, I think one result, which I would say is truly new in this field, is that there's also a growing understanding that AGN not only affect massive galaxies, but they also may play a role in regulating star formation in dwarf galaxies. And this is good news because many models for dwarf galaxy formation need to invoke rather strong supernova feedback. Sometimes this is boosted above the maximum even. It's the efficiencies of 100% or greater. And what people have shown, including one of the organizers, is that the behavior of AGN in these galaxies and of AGN feedback in these galaxies is extremely sensitive to how you model accretion. So if you do Bondi-Hoyle accretion as usual, and you do not boost that, you would have stellar masses which are high, okay? Whereas if you change your black hole accretion model and make it, well, just as plausible, but different, you're actually able to grow the black hole and suppress the star formation or the stellar mass by a large factor. I think it's about a factor of 10. This gives you a visual impression of the difference this can make. So this is a simulation of a dwarf where there's only supernova feedback, and there is a simulation of a dwarf where AGN, where black hole has also grown and boosted the outflow. This behavior is seen in different simulations. So here on the right are results from the Romulus simulation, where in some cases, it's even found that the black hole, the energy injected by the black holes can be dominant, at least in some cases. But these results are I would say this is still in this field is still in its infancy. There are large uncertainties associated to accretion, large uncertainties associated to the dynamics of black holes in these systems, and also to the seeding prescriptions that can all affect what comes out of these simulations. But the message is that AGN may relieve the need for very strong supernova feedback in the dwarf regime. I hope that's okay. So the other advancement in the field is that now various groups have come up with ways of tracking, well, not just black hole mass and feedback, but also the black hole spin. There are different approaches in the literature. Some groups model a subgrid disk, and they model how this disk drains its mass to a black hole. Some groups skip this step, but still try to model how the spin of the black hole is modified through accretion or through torques with the disk. And even more recently, different groups have started using these spins to inform or to guide the spin-dependent feedback, jet feedback strength and radiative efficiency. So here is a case where the spin of the black hole was used to guide the orientation and the strength of the jet. You can see that after some accretion episodes, the jet changes direction and is able to distribute the energy in a more isotropic way in a massive galaxy. Here are similar results or similar approach by Ricardo Beckman in simulations of clusters. And using the spin in this way, plus refinement strategies, we now also have an extremely highly resolved treatment of the jets, which are driven in the centers of massive galaxies. So here is work by Rosie Talbot, where the jet was modeled using the blind photosynthetic efficiency, its direction and the feedback strength were completely coupled to the spin of the black hole. What I think is really interesting is how in this case, so this is a circumnuclear disk. In this case, the jet is actually highly inclined and propagating into the disk essentially, but it still drives this bipolar outflow at large scales. Same is seen here in these simulations by Tanner and Weaver, where this is actually the direction of the jet. You still get a large scale outflow, which is bipolar. And several authors have noticed that this behavior is actually quite similar to quasar feedback, what nominally would be quasar feedback. What happens essentially is you get an energy-driven bubble again. You shock heat this jet fluid, you trap the hot bubble, this expands adiabatically, and then eventually takes past the least resistance. And this is why sometimes you get sentences like this, which are correct, but can come across as complicated. The interaction of young jets in the radio galaxy leads to quasar mode, energy-driven, mechanical, negative or positive feedback. Okay, it's completely correct. To just conclude, can I check how much time I have? Good.
0 time.
Okay, yeah. So to just conclude, I want to mention that there is no AGN feedback if there is no black hole growth. Okay, yeah. And there is no black hole growth if you cannot keep the black holes in the centers of galaxies. And in current simulations, one common approach is to, when the black hole wanders off the galactic center, it's just subtly moved back right to the center of the galaxy. This assumes that the sinking timescale of these black holes would be very short. And there's been interesting work done to show what happens when you vary or when you remove these approaches to place the black holes in the centers of galaxies. So if there's no repositioning, so that's the word people use for this model, then the black hole seeds actually don't grow at all, neither through accretion nor through mergers. So both of these processes are suppressed. If you disable accretion, you can, see that correctly, you can grow the black holes through mergers, but you see that you're still very far away from the default approach in simulations where the black hole is just moved back to the galactic center. So this is a huge effect. And there's been, of course, to solve it, many approaches in the literature that try to model unresolved dynamical friction to make sure the black holes return to the centers of galaxies efficiently. So part of this problem is numerical, because we don't resolve the dynamical friction. However, there's also work showing, and I think there'll be talks about this either tomorrow or the day after, there's also work that shows that a high redshift in clumpy galaxies, these sinking timescales can be long. Okay, so part of this effect could be physical. And then the last point I want to make is when you go to very high redshifts, all these problems come together. So you have small black holes that struggle to go to the center. You also have observationally probably the requirement of super Eddington accretion, which means you may have extremely strong feedback. There has now been various efforts in the literature to connect, to model super Eddington feedback. I would say these are still in the early phases. So here is work by Massonneau, where the efficiency of the jet was connected to the GRMHD predictions. And what's interesting is that even though super Eddington accretion happens, it's completely suppressed by the strong feedback associated to that. So we probably need to think about how we model dynamical friction, super Eddington accretion, and super Eddington feedback. So let's say that's a future direction. And this is what normally we do, of course. Yeah. So, all right. So I will leave my slide with the conclusions.
Right. Thank you. So we have time for a few questions. Yeah, go ahead.
So it was interesting how you were showing that AGN can be quenching dwarf galaxies, But how do I reconcile that with the slides that Daniel showed yesterday, where AGN don't appear to grow at all until the halos achieve a certain mass? Is it possible, for example, that supernova feedback is over-calibrated in those kinds of simulations if you don't account for the AGN feedback component?
Yeah, so there are essentially the literature shows both findings, and I think the differences between them are many. So it's difficult to say, for me at least, which difference is driving this behavior. People have mentioned suggested the supernova feedback treatment could play a role, because in some cases it's hydrodynamically decoupled, so it could make it easier for gas to stay back in and fuel the black hole. In other cases, it's injected locally, which could have a more aggressive effect, which I think is the case in Daniel's talk. So this could be an explanation, but then we would always have to be sure the seeding, the accretion is all modeled in the same way to really make firm comparison, I would say.
Any other questions?
So I was noticing that a lot of this feedback is doing interesting things on like hundreds of parsec scales. And that strikes me as probably observable with like ALMA and maybe even JWST. And I'm wondering to what extent are observations constraining the models?
Yes, so with outflows, it's quite challenging because typically observers trace only one phase of an outflow. So they might see molecular lines or the O3 line, and that is only, that could correspond to a very small fraction of the energy or momentum. On the other side, the simulations often don't have the resolution to make these predictions. So I think we have a problem in comparison between theory and observations. However, one thing that people have tried to do is to measure energetics from observed outflows, momentum fluxes. And the problem there is you find all kinds of behaviors, sometimes energy driven, sometimes momentum driven, and there's no real consensus, I think.
Okay, one last question, and while you're asking it, I'm going to ask Francesco to come up and start setting up.
Hi. So you mentioned about how there's a sinking problem at high redshifts in particular. So black holes can't grow via mergers very efficiently. Black holes can't grow via accretion very efficiently. At the same time, we have these JWST AGNs, which are like overmassive. So do you think simulations will have a problem trying to explain these overmassive AGNs given these issues?
Yes.
All right, let's say.
The first one?
Oh, yeah. Okay, so our first of the contributed speakers, and I'll give you a warning. I'll give you a three-minute warning that when you have 3 minutes left.
Okay, okay.
Not very complicated. Is Francesco Bollati.
Hi everybody, I'm Francesco Bollati. I'm a postdoc at AIP in Potsdam since 1 month. And today I will talk about my PhD project at the University of Insubria in Como. And this is about the connection between AGN radiative feedback and the black hole spin. Okay, first of all, very few words about AGN feedback. AGN feedback can be seen as the release of energy and momentum from an accreting black hole into the environment. And these can occur in different ways. We can have radiation, winds, and jets. And there is observational evidence that these phenomena can have a significant impact on the host galaxy, for example, by driving multi-phase galactic outflows and regulating the host galaxy star formation. And from a theoretical perspective, AGN feedback is invoked in the explanation of many astrophysical phenomena, and therefore nowadays it is routinely included in the semi-analytic and numerical models of galaxy evolution. In this presentation, in particular, I will talk about radiation-driven winds and their impact on isolated disk galaxies and massive black hole binaries. In doing so, I will focus on feedback anisotropy and its dependence on the black hole spin. And with anisotropy, I refer to the angular pattern of the accretion disk luminosity, which in fact varies with the viewing angle. And it does so in a way that depends on the black hole spin. And this is the case because if you increase the spin, the inner edge of the disk gets closer to the black hole. And so the photons emitted by the disk experience a stronger gravitational bending. And in this way, the overall angular pattern is more isotropic. And for example, here you can see the luminosity angular pattern for different spin values. And indeed, by increasing the spin, the angular pattern becomes more spherical. Now, if this radiation couples to the surrounding material, a nuclear wind is launched that inherits the anisotropy of the impinging radiation. And in the following, I will discuss the consequences of this effect. First, I'll present a subgrid model in the code Gizmo that takes into account this spin dependence of feedback anisotropy. In this model, we have a subgrid alpha disk whose properties evolve according to the inflow from resolved scales and the accretion within the disk. The accretion in the disk also sets the mass outflow rate, and this is performed by spawning gas particles, and the mass distribution of the particles follows the luminosity angular pattern. Then these particles are kicked outward and they generate an outflow. And overall, this subgrid model self-consistently tracks the resolved accretion, black hole mass and spin evolution, wind launching, and its anisotropy. Now I'll present a first application of this model. I considered an isolated galaxy hosting a black hole, and for this was supposed to be a movie, but okay. Okay. And this galaxy is formed by the collapse of a spinning gaseous halo. And in these simulations, I considered two sets. No, stopped working. Okay.
Does it work on your screen? Oh, I guess that's the only other screen.
It's not going on with the, I don't.
I mean, is it? Last. You. Oh. I did nothing.
I can also see.
Yeah, you might have
Obviously, I
to.
don't know that password. It's right on the keyboard if you're.
All right. I'll let you get back to where you were.
Yeah, hopefully it works.
It's crossed.
Okay. Okay. So in these simulations, I consider two sets. In the first set, the accretion rate is forced. The subgrid accretion rate is forced to be constant and equal to the Eddington rate. While in the second, the accretion rate is allowed to vary. And in both sets, I consider the different feedback angular patterns. That is maximally anisotropic, isotropic, and with anisotropy that evolve according to the spin. Now we can show some results. First, we found that accretion and feedback regulate each other in the sense that feedback limits the inflows that power itself. And so when this self-regulation is enabled, that is in this case, we have that the accretion rate on the black hole drops and attains values that are typical of Cepheid galaxies. Now, if the accretion decreases, then also feedback becomes weaker and the overall impact on the host galaxy is less pronounced. For example, with Eddington accretion, we see that the morphology of the galaxy is severely altered by the presence of feedback, while it's not if the accretion is feedback regulated. In particular, in such cases, we have that the size of the central cavity cleared by feedback is about 1 order of magnitude smaller compared to the other simulations. Similarly, if you look at the galaxy star formation rate, we see that in the first case, it is reduced of about a factor of 2 compared to the other simulations, in which the star formation is almost undistinguishable from that of a simulation without feedback. And this means that a galaxy can host luminous AGN activity without any significant impact on its global star formation rate, and this is something already found in observations. Then the imprint of different feedback angular patterns is found only for Eddington accretion, and in particular, the more isotropic is the angular pattern, the more easily winds sweep away the ISM, and this results in larger cavities and in more star formation suppression. Similarly, more isotropic winds also cause a slower black hole mass and spin growth. And this is because they remove more efficiently the gas that accretes from the black hole. But actually, we saw a very small hint of this trend. To summarize this first part, we saw that for higher black hole spin, we have a more isotropic feedback angular pattern, and this can translate into higher star formation suppression and slower black hole growth. And the sensitivity to the feedback angular pattern can be better appreciated at a higher accretion rate and for more spherical geometries of gas around the black hole that enhance the ISM and wind coupling. And both these conditions are likely to be found in post-merger and high redshift galaxies. And finally, we can speculate that low spinning massive black holes are more likely to enter a super Eddington accretion regime because they are less prone to alter the accretion in the equatorial plane. Now I'll discuss a second application in the context of massive black hole pairs and binaries. In a previous work, I studied the spiral of black hole pairs at tens of parsec separation embedded in circumnuclear disks. And I showed that different feedback models in terms of anisotropy and direction can produce very different dynamics. But in this work, I used a less refined feedback model in which the anisotropy is a free parameter and is decoupled from the spin value. Now, at smaller scales, when the black holes are bound and form a binary, it has been shown that isotropic feedback is capable of clearing a cavity around the binary, and this cavity can prevent the black holes from migrating. Now, a question is whether anisotropy can attenuate this conclusion, and in general, which are the effects of anisotropy on the binary evolution. So to this purpose, I consider this following setup, consisting of two equal mass black holes at 2 parsec separation embedded in a circumbinary disk. And this time, the size of the subgrid accretion disk can be smaller, can be comparable or larger compared to the smallest resolve scales. And in this case, therefore, accretion is performed via particle capture. And we consider the different spin configurations in terms of moduli and inclinations, and also different binary masses that without feedback correspond to different binary migration regime. I can show you one of these simulations. In the face-on view, we can see the formation of mini disks around the black hole. And in the side-on view, there is the ejection of wind in the polar direction that also tend to flatten the disk in the nearby the binary. And now I can just give a sketch of some preliminary results. We can distinguish two main behaviors depending on whether feedback clears a cavity or not. And this, due to feedback anisotropy, depends on the spin's inclination. So in the first case, we observe orbital expansion, whereas in the second, we have orbital stalling. But in no simulation, we have binary migration in the presence of feedback. Then we also see that in the first case, the accretion through the subgrid disks is continuous, while in the second case, accretion is bursty with a duty cycle that depends on the spin orientations. And finally, if there is no feedback cavity, the accretion on the black holes is coherent, while in the other case, the accretion episodes tend to be misaligned with respect to the direction of the spin, and therefore these accretion events cause a erratic spin direction evolution. And that's it. I leave you with my conclusions. And thank you very much.
Thank you. Thank you for persevering through some erratic PowerPoints. Questions? Thank you.
Thank you for this talk. So I wanted to ask about the accretion disk modeling. So yes, the second part of the talk, how do you model the viscosity, and also how long do you run these simulations to look at the orbital migration?
Okay, viscosity is, okay, this model is based on work by Davide Fiacconi, 2018. And the underlying assumption is that we have an alpha disk. Actually is the C part of the alpha disk, the more external one. So starting from these scaling relations of alpha disk, he found a semi-analytic expression that gives the accretion rate from the total disk mass, total angular momentum, and black hole mass spin. And so the Shakura-Sunyava assumption and viscosity enters in this expression. And for how long I have to simulate in order to see migration? Okay, in the simulations without feedback, in which we do have migration, it was about a few mega years, because it was just a few orbital periods, and the orbital periods was I don't remember, like 0.1 mega year. So these were the timescales.
Okay, thank you.
Thanks, very interesting. So I understand that when you inject the winds, then the geometry follows that of the radiation field, which depends on the spin. So what I miss is, how do you determine the mass outflow rate and the velocity of the winds? Are those parameters of the model, or what determines?
Yes, the velocity of the wind is a free parameter, because the mass is just computed from the accretion rate. And so I know each time step how much mass I have to go into winds, but then the velocity is just fixed. In this case, it was 0.01 the speed of light.
But for the mass outflow rate, should you use the same as the black hole accretion rate?
No, it is proportional to the black hole accretion rate, and the proportionality is found by requiring that the momentum flux of the radiation is completely transferred to the gas. Okay. And in this way, the coupling between the mass outflow rate and the accretion rate is the radiative efficiency times speed of light divided by velocity of wind.
Yeah, thank you.
Okay, let's thank Francisco again. The next contributed speaker is Kang Isu.
Hi everyone. Thanks very much for having me here. I'm Kong Isu, currently a postdoc at Black Initiative at Harvard. So today I'm going to talk about some previous and ongoing work about like suppressing cooling flow with cosmic ray in the jet cocoon shock front. So we know that in the massive galaxy and in cluster ellipticals, there's cooling flow problem, which means that by the predicted cooling flow from the extra luminosity we see, the predicted cooling flow will be too high compared with the star formation rate in this galaxy. This galaxy are typically quenched. So if all the predicted cooling flow for in the center of the galaxy and form stars, the star formation rate should be orders of magnitude higher. So this tells us that there must be some sort of heat source or pressure support that could compensate the cooling flow. And as we know, a very promising candidate of that will be the AGN feedback in the form of like AGN jet. However, we know that in the galaxy simulations, as we have established, that a lot of them, most of them actually require subgrid model, which means I have effective accretion model, like a Bondi type model or like a gravitational torque model, and just deposit certain fraction of the accreted mass and energy in the form of AGN feedback. However, the actual form of the AGN feedback or even the form of the jet, even the energetic is highly uncertain, and so as the whole AGN feedback model. So previously we've done a very wide parameter study of the injection part of AGN jet, vary a lot of like the energy composition, energy flux, mass flux, and so on and so forth, and also have a subset of more successful model around 10 to 12, 10 to 15 solar mass. And from that, we conclude a few criteria for a more successful AGN jet model. So one of them will be that cocoon have to be wide enough, and also the cooling time of the jet within the AGN jet cocoon has to be long enough. So with this, given a high enough energy flux, it could quench the galaxy. And also following that, we see a few category of like more successful model could fulfill these criteria. One of them is cosmic ray jet, if majority of energy in the cosmic ray, and also like a possibility is like thermal, very hot thermal jet. Like with temperature higher than a few times 10 to 9 Kelvin. And also like the possibilities will be like high specific heat kinetic jet with widely precessing or wide open angle. And as you can see from the star formation rate from 10 to 12, 10 to 15 solar mass, even sufficient high energy flux, all of these models will quench these massive galaxies. And in particular, I want to highlight that the blue lines and the cyan line here, that given the same energy flux, cosmic ray jet could always quench most efficiently. And the reason we found previously is that the cosmic ray pressure support and also the change of thermal instability. So by providing this extra feature, that cosmic ray actually quench most efficiently. However, so for example, these are a few runs with cosmic ray energy dominate jet from a few times, so for 10 to the 14 solar mass case, for example, starting from a few times 10 to 42 Earths per second, you can start to quench this massive galaxy. And this is the movie of that. On the right-hand side is the cosmic ray pressure. And as you can see, the cosmic ray pressure do build up a extended pressure profile to a few 10 kiloparsec. And that pressure actually helps suppressing the cooling flow, and which in turn suppresses the star formation rate. So, however, there's a few potential problem with the cosmic ray energy dominate jet. So if the most of the jet energy is in the form of cosmic ray, it very easily results in excessive gamma ray flux, especially for the most massive halo mass case, like the 10 to the 15 solar mass case. And also the traditional way of injecting cosmic ray does not necessarily inject cosmic ray at the shock front, which is most likely the position that the cosmic ray is accelerated. So here in the subsequent work, we try to ask the questions that how should we actually inject cosmic ray? Should we actually inject in the traditional way that inject cosmic ray at a black hole vicinity, or like we inject cosmic ray more or less at a jet cocoon shock front? So to give you more detail, so we're using particle spawning method for launching AGN jet, which means that we're spawning gas particles from the black hole to model the jet. And so when a jet particle is created, we can assign a mass, velocity, temperature, magnetic field, and also cosmic ray. So this will more or less give you a mass flux, momentum flux, energy flux, and cosmic ray energy flux. So the motivation of trying to do this original way is that these cosmic rays try to capture the sub-resolution physics that is not applicable to capture in this galaxy simulation. So for example, the cosmic ray from the subgrid shocks or something like that. However, taking advantage of particle spawning method, you can also easily do like inject cosmic ray at a larger scale jet cocoon shock front. So here we have a toy model that when the jet particle is decelerated to 1/4 of the initial velocity, we say more or less have already encountered a strong shock, and we just inject cosmic ray there. And the motivation of doing so will be that it's try to capture the cosmic ray accelerated by the larger scale shock front. So that can see have a very huge effect in the resulting cosmic ray profile and the jet propagation. So for example, these are two of the constant energy flux jet, but with 0.1 energy injected either at a black hole vicinity or at the larger scale shock front. So the upper panel here is a cosmic ray pressure profile. Immediately see like a difference between the cosmic ray energy density. Like if you inject cosmic ray at a larger scale jet cocoon shock front, you have a much more prominent cosmic ray distribution extended to a larger radii. And also, you can see that there's a sharper transition within the jet cocoon to the outer part, that there's more cosmic ray in the jet cocoon and sharper transition from that to the ambient medium. And also those positions roughly coincide with the region that we have the shock. So the bottom panel is a radial velocity profile. Red is inflowing and black is outflowing. So you do see that the cosmic ray is roughly injected at the shock front. And if you further play the movie, you do see that this bright region, those are the shock region and where we inject cosmic ray. And also, if we also like try to test the inject cosmic ray at the shock front method and couple with different kind of precession. So the left-hand side, this is a run. So all of them has 0.1 of energy injecting cosmic ray and at a shock front. Left-hand side, this is no precessing, and this has a longer time period precession, 100 million year. And the right-hand side is the run with 10 million year precession. Again, the upper panel is cosmic ray pressure profile. The lower panel is radial velocity. Again, red is inflowing and black is outflowing. So immediately see that the change of the precession actually change the location of the shock. And if you deposit cosmic ray at a shock front, that in turn changes the eventual cosmic ray distribution. So for example, if there's no precession at all, the shock front is keep pushing further and further. And then a lot of cosmic rays deposit at pretty large radii. And on the other hand, if you have some level of precession, a lot of cosmic rays retain in a few 10 kiloparsec. So that has a non-negligible effect of the resulting star formation history. So left-hand side, the star formation history, it's a function of time. The right-hand side is density, temperature, and cosmic ray pressure profile. So first, if we first see from injecting cosmic ray at a black hole vicinity, which is the blue line, versus injecting cosmic ray at a shock front, which is the red line, you do see with the constant energy flux jet with sufficient high energy flux, both of them could suppress the star formation rate. However, they lead to very different density and cosmic ray pressure profile. So when you inject cosmic ray at a black hole vicinity, it suppresses density in the core region of the black around the black hole more, and also it has a much more cuspy distribution of the cosmic ray, like the blue line here. On the other hand, if you inject cosmic ray at a larger scale cocoon shock front, it tend have a much more flatter distribution of the cosmic ray, and a lot of cosmic ray is actually located at a few 10 kiloparsec. And also changing the jet precession also changed the resulting star formation history and also the cosmic ray pressure profile. So for example, if there's no precession at all, like the pink line here, a lot of cosmic rays deposit at a very, very large radii, and that doesn't have a huge effect on the star formation rate. On the other hand, if you have some level of precession, a lot of cosmic ray, as we see, is deposited at a few 10 kiloparsec, which is maximum, is the region that a cooling flow is maximally happen, and that in terms like the red line and magenta line here has a maximum effect of the star formation history. So far I only talk about the constant energy flux jet. So how about when we turn on accretion? Yeah, how does the accretion couple with different way of injecting cosmic ray? So it turns out that accretion, the different way of injecting cosmic ray actually matter even more when you turn on accretion. So again, there's two categorical model: inject cosmic ray at black hole vicinity versus at larger scale shock front. But now we turn on gravitational torque accretion, and this is a resulting profile. Like so, these two runs are injecting cosmic ray at black hole vicinity. This is a cosmic ray dominant jet. The central part is the case with 0.1 energy inject at the black hole vicinity, and the right hand side is the case we inject 0.1 one of the energy in cosmic ray at a larger scale shock front. And if you play the movie, you immediately see the very huge difference. If you inject cosmic ray at black hole vicinity, resulting in much more episodic distribution of like episodic energy flux of the jet due to the very much episodic accretion history. On the other hand, if you inject cosmic ray at larger scale shock front, it has a much more sustained energy flux throughout the simulations time. And also that leads to a much more extended cosmic ray distribution. And furthermore, it's actually possible to quench the massive galaxy. So this is a run with 0.3 of the energy injected cosmic ray at a larger scale shock front. And the resulting star formation history is like a blue line. You see this like episodic duty cycle of quenching history over like a few 100 million year to 1 giga-year time scale. And also, if you see the black hole accretion history and the energy flux of the jet, when you inject cosmic ray at the shock front, like the red line and the magenta line here, you do have a more sustained energy flux of the jet and also more sustained longer duty cycle of the black hole accretion history. On the other hand, if you have cosmic ray injected at black hole vicinity, resulting in like the red line and the green line here is very episodic accretion history and very episodic jet energy flux. And also similarly, do you see the, when you inject cosmic ray at a black hole vicinity, do you see like a more episodic large decrease of density at the black hole vicinity, which leads to this episodic behavior of accretion history. So to summarize, I'll quickly go to that. We have Tesla cosmic ray is very efficient in quenching the massive galaxy. And actually how we deposit cosmic ray actually matters. When we deposit cosmic ray at a larger scale shock front, it has more extended cosmic ray distribution, longer duty cycle, and also on average higher energy flux. And that is more effective in quenching. Also the jet precessing coupled are near to that. And also the jet precessing actually change the location of the shock front. If you deposit cosmic ray at those shock front, it changed the cosmic ray distribution. And some sweet spot of few 10 million year precession, they have maximum effect of suppressing the cooling flow and quench these massive galaxies. So I'll stop here and take any question. Thanks.
Thank you, Kung. Questions?
Thanks for the nice talk, Kungi. I was wondering, because you mentioned at some point about the cosmic ray constraints coming from an excess of gamma ray emission. I'm wondering, are the models that you've tested here, would they all be consistent with the gamma ray observations that we have?
So I think the most constraint of gamma ray flux is from like the most massive 10 to the 15 solar mass-ish halo. With that, I haven't run this cosmic ray injected shock front in 10 to 15 solar mass. Those are more expensive, but from what I see, the cosmic ray distribution is much denser, and that definitely would definitely lower the cost, the gamma ray flux if I do that in 10 to 15 solar mass. But that is not tested yet, and also hope that will partially reconcile that problem. Yeah.
Other questions?
I wonder about the free parameters in your cosmic ray feedback. So in relation to other standard supernova feedback models or Asian jet simulation, for CR importance, do you still think that there's enough room to play around in those free parameters about relative importance, or your opinion is that CR is really definitely more important than the other possible channels?
So I think there's definitely other way they could possibly quench the galaxy, but I think what we found is that there's, when we have cosmic ray, it somehow allow a wider parameter space that could quench these massive galaxy. And I think the parameters will vary for the cosmic ray, like from in the later model that was inject cosmic ray at a shock front, like 10% to 30%. Those are possibly within the reasonable region for like cosmic ray, also consistent with what people do for the supernova feedback and other things like that.
Okay, if there's no other questions, let's thank Kengi again. Okay, use that.
Okay, yeah, thanks. So I'm Martin Bourne. I'm a postdoc at the University of Cambridge, Institute of Astronomy. And I've decided to talk on a few different things today, which is why I have a somewhat broad topic of simulating supermassive black holes. And this is all work that I've been doing over the last however many years with this bunch of people here, mostly working with Deborah Shiatsky's group in Cambridge. So, yeah, this is probably the third time we've seen this motivational slide on why we need supermassive black holes, or in particular the feedback from them in terms of how they shape galaxies, groups, clusters, how they might regulate their own black hole growth, enrich the CGM. I think, you know, as I'll talk about later, particularly in galaxy clusters, they seem to be important for regulating the thermodynamics. And more recently, also a lot of interest in the effect they have on the matter power spectrum when we're looking to do cosmology with, for example, weak lensing observations as well. So again, this is probably the umpteenth time we've seen something like this as well. When it comes to simulating supermassive black holes, one of the big challenges is the vast dynamic range that we're covering, and this is, you know, one of two of the key motivations for the work that we've been doing. So there's the physics side of things. We want to learn about black holes and what they're doing in terms of galaxy formation, multi-messenger astronomy, and things like this. And then there's also developing techniques to try and overcome, you know, this range that you can't capture in a single simulation, but how can we start to bridge the gaps? So first of all, just a couple of techniques that we're employing for our works. And I think this is becoming a very popular technique now. So this, we had within a repo, we had a black hole refinement scheme, or a super Lagrangian refinement scheme that was developed by Mike Curtis, who was one of our previous PhD students. And essentially, if you have a black hole in the center here, you have some refinement region, and you progressively improve the spatial resolution as you get close to the black hole. This was done to, you know, resolve the Bondi radius and better capture, you know, accretion rates onto the black hole. But it was also found that if you include it in, say, a cosmological simulation here, you also get very different morphologies for the feedback. This is just standard thermal dump, but with the improved resolution, you get this very dense cold disk here, and this sort of naturally arising bipolar outflow. Then the other model that we use quite a lot in what we've been doing recently, and we had about this model a bit in a talk a couple of talks ago, is a subgrid Shakura-Sinyaev accretion disk. So essentially, instead of just having a black hole particle, you have a particle that's split into a thin accretion disk, a central black hole. You track the black hole spin and mass, and you track the angular momentum and mass of the subgrid accretion disk. And if you assume it's a Shakura-Sinyaev disk, you can have a nice analytic model that evolves the system, and you can couple it to the resolvable scales through mass and angular momentum inflows. And so now I'm going to talk about a few projects that combine these things and add a few new things as well. So recently, I've been looking at modeling supermassive black hole binaries in self-gravitating circumbinary disks. Over here is an illustration where we include this refinement technique around the black holes, which allows us to capture the mini disks and the streams feed these black holes. And these have an appreciable effect on the gravitational torques felt by the binary, and an effect on the binary evolution. So because we can now capture the torques that you get not only from the circumbinary disk, but also from the filaments and the streams and the mini disks. And you can see the torques in these maps down here. So these are just average torque surface density maps. We've run a range of different types of binaries and a range of different mass ratios. We've done retrograde inclined binaries. When we look at and in all cases for the simulations we've done, we find that the binaries shrink. So we're moving towards merger, which isn't the case. You know, there's a whole bunch of simulations that have been done using different types of models for thermodynamics and with and without self-gravity and things like this that can affect the binary evolution. But in our case, they all shrink. And then the inclusion of the subgrid accretion disk model means that we can also track the black hole spins during this process. And so if you have a Shakuris and you have accretion disk, you can calculate the timescale on which the black hole spin aligns with its own accretion disk. And there was some analytic work by DeRosa back in 2015, where if you assume a coplanar system, if you assume that the spins align with their own accretion disks, then and the accretion disks are aligned with each other, and the spins are aligning with each other. If they did some models assuming preferential accretion onto the secondaries with this red band and this blue band here for the primary black hole, and compared this to the inspiral time for the binary, and they found that for low mass ratios, because you have preferential accretion onto the secondary, your primary doesn't accrete enough, and so your spin might not align on a short enough timescale. In our simulations, we don't actually find preferential accretion to the secondary. We get preferential accretion onto the primary. This is most likely related to the thermodynamics and the viscosity treatments. But this means that we get spin alignment on short timescales, even for the primary black hole at low mass ratios. The caveat for our work here, though, is that we've also done runs where we have binaries that are inclined with respect to the circumbinary disk. And if we look at the angular momentum, so the blue dots, for example, on here that are going all over the place, is the angular momentum of the mini disk that's feeding the central black hole. This is wandering all over the place. And this is because the mini disks, when you have an inclined system, don't align on particularly short timescales. And this was seen in some other simulations, I think by Moody as well, who's done these inclined systems. And the reason that having spin alignment, and trying to look at spin alignment is important, is because if you have misaligned spins when it comes to merger, you can have high recoil velocities for the merger remnant. And if these are high enough, you might kick your black hole out of the system. Okay. So that's the first project. I'm going to shift on to a slightly different topic now and look at feedback. So we heard in the previous talk about jet feedback. I think this is most obvious in galaxy clusters and high mass systems where you have this hot X-ray emitting intracluster medium, and the jets inflate these lobes and cavities within these systems. You have, for example, Perseus in here, which is probably sort of the poster cluster when it comes to looking at these sorts of things, where you see these old cavities and effects as well. Here, the bubbles are common in systems with the shortest central cooling times. Well, that might be some observational bias in there. But I think the key thing is that if you estimate the power to inflate these cavities with the cooling rates within the systems, you get this tight correlation. You get this correlation between the two that's normally taken as evidence that the feedback is regulating the cooling within the intracluster medium. While the energetics way up, there's still a number of open questions around how the feedback actually heats the ICM. These are all sort of hydrodynamic processes, whether it's shocks or sound waves, gravity waves, mixing, turbulence. There's a whole bunch of other things you might want to include if you're trying to simulate these things. We heard about cosmic rays in the previous talk. Jet precession, direction, thermal conduction. The jets are really relativistic, but not often modeled as relativistic in these sorts of simulations. You have the effects of magnetic, so on and so forth. I'm going to shamelessly plug a recent review article that Karen Yang and I put out earlier this year. But one area I've been particularly interested in is looking at the effect of the environment and the cluster weather. So, gone too far. Let's go back. There we go. So again, within a repo, using the refinement scheme, I developed a jet model where I can inject the jet at high resolution on small scales, and we take the resolution with us essentially, so we can have these low density cocoons, fast jets up to very large scales. And then we've implemented this into a cosmologically evolved cluster environment. For now, just doing fixed power jets over a fixed amount of time. So this yellow box here is this point in the center of this cluster, and we can look at the lobe inflation and interaction with the cluster weather. So it's just illustrating the Voronoi mesh within this region here. There's also this cold disk structure in the center that the jet interacts with. Here's a quick video of what's going on. I apologize for the color scheme, but you have this jet material in green, then you have the hot sort of mustard color and the colder material in pink. And you can see that the dynamic environment of the cluster is shifting the lobes about, disrupting lobe mixing material. We've done this for a few different jet powers, qualitatively similar behavior. You can do mock X-ray images and try and paint on some synchrotron emission to see what sort of morphology you get. But this is really just very qualitative on this side, nothing to look at the sort of shapes we see. We look at the energetics then. We get the sort of, I think what's seems to be a fairly common picture now, that during inflation, half the energy is in the lobes, half the energy then goes into work done on the environment. You know, this can be through shocks, displacing materials, some mixing. We find that the low power jets are more susceptible to being mixed with the ICM. The higher power jets, as you expect when you have more rapid lobe inflation, end up driving stronger shocks. This is illustrated here. So the high power jet, we have stronger, longer lived shocks. Even after the jet's turned off, you have some residual motion of the cocoon that's driving shocks in this case. They were done without magnetic fields. We're now running them with magnetic fields in the cluster. And I think the main thing I just want to show is this one over here, given the time's slowly running out. But you can see the difference with magnetic fields and without magnetic fields, the difference in the lobe structure. The magnetic fields suppress the instabilities that end up mixing your lobes. The lobes live longer, stay at lower densities. And so this affects, therefore, where the energy can be deposited, although this is very much ongoing work that needs looking at more. Then we want to try and combine these a bit more. This is, Tiago already mentioned some of this stuff from Rosie Talbot, essentially coupling the jet feedback model to the subgrid accretion disk model, and having a spin-dependent efficiency for the jet feedback based on the Bamford-Snack mechanism, taking this from GRMHD simulations. Here we have a jet that's just firing directly along. This is the jet that was initially firing into the circumnuclear disk, creating this multi-phase outflow, and then the jet is being torqued, or the black hole spin is being torqued, which is redirecting the jet slowly as we move up. Very quickly, this has also been used in merger simulations as well. And then the last thing, maybe not, or maybe I won't. It knows my time's up.
Why don't it looks like it's crashed again.
Okay, I'll stop there.
Why don't we stop there and thank Martin. Let's take some questions.
Hi, Martin, that was great. So I have two questions. One of them is, you show these mock radio images. Was this synchrotron or
yeah, it's
how
just,
did you model that?
just synchrotrons, but yeah, we don't have magnetic fields and we don't inject cosmic rays, but we have a jet tracer, and then we make some assumption about the magnetic field morphology, what fraction of the energy is in the magnetic field, what fractions in the cosmic rays.
Okay.
And then paint on synchrotron.
All right, and just if I can ask a second question. So the jets, you showed a lot of jets, so I don't know which ones my question applies for, but are these light jets or heavy jets, and does that matter?
These are pretty light, fast jets. Yeah, and it does matter, right? If you have a heavy, slow jet, this just punches through, and will go to very large distances. The faster lighted your jet is, you can get these wider lobes. As we heard in the previous talk, this can
thermalizes at small scale.
make a big difference in how and where the energy is communicated, and also how much the jet might be deflected by the environment and things like this.
Let's take another question. And actually, I'm going to get you shipped aside. I'm going to try and work on this, the AVC here.
Could you go back to the slide that you didn't have time to present?
Sadly,
I think on the Bamford-Snack mechanism.
I'm not sure if I can go back to
Thanks.
Crash? Yeah. Brings up my Spotify.
Well, what can you say about that slide? Nice plan.
Yeah.
For powering jets.
So the one that Chris, oh, that was the Galaxy Merger.
Yeah.
Yeah, so we were including this model with in a Galaxy Merger simulation. So the yep. So the jet direction and the efficiency were dependent on the black hole spin, and you can get an efficiency spin relation from GRMHD simulations. So for these simulations, the black holes were the spin was initially directed out of the galaxy. And it stays for that a lot of the time. But one of the interesting things we saw there was that the jet feedback can promote the formation of cold gas in the halo that rains back down. And this material ends up torquing the black hole. And actually the black hole spin then ends up shifting towards the disk.
Right. I think Donnie and Boyd had reported a result where the energy injected into the intercluster medium was always around 3 × 10⁻³ times the mass of the black hole. Does anything like that come out in the simulations?
I haven't looked at that specific quantity. But yeah, it's something to look at.
Thanks.
Okay, let's thank Martin again. And our last, but certainly not least contributed speaker will be Erin Cho.
Hi, everyone. I'm Heron Cho. I'm a 4th-year grad student at CFA. My advisor is Ramesh Narayan, and today I'll be talking about bridging scales in black hole accretion and feedback. This paper has been recently accepted to FJ letters, and you can also find it on arXiv. Okay, so in studying black hole accretion and feedback is very important, and its impact on larger galactic scales is especially important when we want to understand black hole and the galaxy coevolution. And we have 2 simulations tools to study that. One is galaxy simulation with Newtonian gravity, where the best resolution is usually around 10 parsec, and that corresponds to 3 × 10⁴ gravitational radius for M87's case. And there is GRMHD simulations simulating close to the black hole. And because it's very computationally expensive, it usually only converges up to 100 RG. So it has been very challenging to study the interaction between small scales near the black hole and the large scales of the galaxy and how they communicate in both directions for accretion and feedback. So I wanted to go over why is it so hard to simulate the black hole plus galaxy system in just one simulation self-consistently. And we can look at the scales that are involved. In the middle, we have a black hole where the smallest length scale is around gravitational radius. And then there is a boundary radius, which is around 10⁵ times of that. And then the largest scale, 1 megaparsec would be around 3 × 10⁹ gravitational radius. If you want to study this whole, if you want to simulate this whole system at once, the time step would be determined by the smallest length scale near the black hole, which is around the few gravitational radius by current condition. However, the total runtime that we have to run the simulation up to would be determined the largest length scale that we want the conversions up to. So if we assume that we want a simulation that converges from the event horizon all the way to the boundary radius at this given resolution, it's going to take me around 13 years, around 15 years to complete, which is very impractical. There has been recent attempts to bridge the galactic scales to the horizon scales using different methods. And they have been very successful at tracking the inflow or accretion or advection of energy from largest to the horizon scales. However, to the best of our knowledge, there has not been a simulation going from the black hole to the galactic scales tracking the other direction, which is the outflow or feedback self-consistently. We have came up with this new method in order to solve this problem, which we call the multi-zone method for hot accretion flows case. This is using a GRMHD code called Karma. So the idea is that if we have a very huge spherical grid going from the black hole horizon to say 10 to the 8 RG, instead of trying to simulate the whole thing, which is impractical as we've shown, we would divide it into different annuli, evenly spaced in log R, and we would only keep one active zone. We would only simulate one active zone at a time, while freezing any other zones fixed. So this is the video that's demonstrating this method. So we would only have the active largest zone simulate for some amount of time, then we'll switch to the next overlapping zone, neighboring zone to simulate, and then so on and so on until we reach the black hole. And then we would go back out again, we'll slide this active zone back out again, and we would repeat this in and out multiple times in order to track both accretion and feedback at the same time from the horizon to galactic scales. Since we came up with the new method, we didn't want to apply this to a realistic or very complicated systems, but we wanted to test this out in the simplest case possible. So we decided to run the hydrodynamic Bondi accretion with black hole spin of 0 and no angular momentum of gas. This problem is specifically good because we exactly know what the relativistic solution is analytically. So we can compare our simulation results with the analytic solutions. So here I'm showing the simulation result along with analytic solutions in, so analytic solutions are shown in thick gray line, and the simulation hydrodynamics results are shown in red line. You can see that in the first panel, that's density as a function of radius in gravitational units from 2 RG to 10 to beyond Bondi radius, which is around 2 times 10 to 5. And the upper x-axis is showing the radius in physical units. The density is following our density is perfectly agreeing with the analytic solution, which is characterized by r to the minus 3/2 inside the Bondi radius. And And then on the right panel, there is a feedback efficiency parameter where if it's a positive value, it means there is feedback from the black hole horizon to the galactic scales. And if it's a negative value, there's no feedback and there's only an advection of energy coming from the galactic scales to the horizon. So the dotted lines means that's a negative value, meaning both analytic solution and our simulation results agree that there's no feedback in this case, and the amount of affected energy both also agrees with each other. So this is a very simple problem where the only direction of information is coming from the largest scale to the black hole horizon. However, the real challenge would be when we add very strong magnetic fields, where the system would go become very highly turbulent, and there will also be outflow along with inflow. And our method would be able to capture both outflow and inflow and accretion and feedback. So we've also added the strong magnetic fields onto the black hole, Bondi accretion, which I call a mad version of Bondi because it is actually magnetically saturated. So here I am showing the accretion rate onto the horizon as a function of time. The accretion rate is in units of the Bondi accretion rate, and the time is in units of the free fall time scale at the Bondi radius, TB, which is around 76 kiloyears for M87. You can see that after a few TB, the accretion rate onto the black hole fluctuates with respect to a constant value of around 5 times 10 to the minus 3 of the Bondi accretion rate, which is consistent with observations. And here I show the snapshot of the simulation. So it's showing from the smallest zone going to the largest zone. And if you look at the scale bar, you can take a look at what each zone's length scales are. Left half of each panels are showing the plasma beta parameter, and the right half is showing the density with the magnetic fields overplotted. In this specific snapshot, you can see that we have captured the moment of a very strong outflow, which you can see in zone 4. So you can see that when even though we only added magnetic fields to the Bondi accretion's case, Now the system has become very turbulent and has a powerful outflow. We can repeat the same analysis as before, looking at time average radial profiles. So the new MHD run is shown in black. The density has changed its slope to r to the -1, consistent with Wenrui's yesterday talk and also EHT and X-ray observations. And also, if you look at the right panel, the feedback parameter now has changed its sign to a positive value, meaning that with addition of magnetic fields, there is now feedback from the black hole to the galactic scales. And the amount of feedback is around 1% of the accreted rest mass energy, or with respect to the Bondi accretion rate, that would be 5 times 10 to the -5 of m dot b c squared. We are originally very surprised to see this result because we're not expecting any feedback when we don't have black hole spin or gas rotation. So this, we have reported a minimum amount of black hole feedback, because when we add black hole spin or gas rotation, the feedback will only increase from here. We went even further to look at what is the dominant mechanism of this feedback. So we can divide the feedback efficiency parameter into two different contributions. And you can see that the blue is the contribution coming from the fluid, and cyan is coming from the contribution from the electromagnetic fields. And the contribution from fluid is completely dominant. And we can even divide this further by looking at advection component versus the convection component, where the advection component is more looking at the laminar flow of energy, or convection is more turbulent energy flow. And the convection component, which is shown in red, completely dominates over the advection part, which is in green. So from this analysis, we have concluded what the feedback that we are seeing in this case is driven by convection, which is initially initiated with reconnection events. So I'll end with the summary. We have been able to study accretion and feedback using our multi-zone method. In hydroid case, Bondi case, perfect agreement with analytic solution, no feedback. When we add B fields, the density changes slope to r to the -1, and accretion rate is suppressed from the Bondi accretion rate. There is feedback even in the absence of black hole spin or gas rotation. In the future, instead of initializing from arbitrary conditions, I would like to initialize our outermost zone with gizmo simulations provided by which will be provided by Kang-Yi. External gravity from all of these components, radiative cooling, and so on. And on top of that, I'm very excited to add black hole spin and angular momentum of the gas to provide sub-prescriptions for cosmology simulations, such as jet or MHD winds. That would be very self-consistent prescriptions. So stay tuned. And ultimately, we would like to make a library of self-consistent black hole galaxy simulations, such as what CAMELS is doing for cosmology simulations, as we talked yesterday. So thank you very much.
Thank you very much. Questions?
Thank you very much for your excellent talk. So I have two questions. One is that, what's the real reason of the scaling, new scaling? Is that due to the CDO magnetic field, or basically, even if you do a hydro but with some small turbulence or perturbation to drive your turbulence, then you would get the similar radial profile?
Yeah, that's what we're also trying to investigate. So I've read your paper on your purely hydrodynamic case with jitter, and you found r to the -1 slope. So we were trying to reproduce that right now. I'm running that simulation, so I'll be able to get back to you soon. But I think what we are seeing is also very similar to r to the -1. So I think it's a good question whether or not this r to the -1 is because of magnetic fields or the turbulent behavior of the gas. So yeah.
Thank you. And the second question is that here there's no rotation, right? But if we add rotation, I was wondering that in the boundary there would be a strong share between the inner region which is fixed and your outer region which is active. So how would you handle this problem, or is that a problem?
I think that could be a problem. We haven't really ran simulations with strong angular velocities in our simulation. So I think I'll have to actually run the simulation to find out if it's a problem for us or not. But I think that could be a solvable problem if we set the runtime for each zones. If we control the runtimes for each zones before switching, I think it could be solved, but I think I'll have to actually simulate it first.
Yeah, thank you very much.
Thank you.
Other questions?
Right, thanks for a great talk. So there's this simulations called the Forge It in Fire, where we combine the fire simulations with the StarForge simulations.
Oh, no. Oh, sorry.
No, I was just
okay.
mentioning that in there, obviously they might be having much larger scales compared to your simulations, but they find that when you add magnetic fields, it aids gas and flows, suppresses self-consistently star formation at larger accretion disk scales. So overall, I was wondering if in your case, obviously you see the magnetic fields are suppressing accretion. And so overall, I was wondering if in general, like magnetic fields, do they aid accretion or suppress accretion, because you have two different results coming from simulations, two different types of simulations.
Definitely what we're seeing here is that it is suppressing accretion. I think it also might depend on how strong your magnetic fields are, especially in magnetically saturated simulations. We often see that accretion is suppressed by the strong magnetic fields trying to block, preventing gas to come in. But yeah, I think that's an interesting question, but which I don't have an answer to. But it could be different when we add the spin of the black hole. It could, this accretion could change, the accretion rate could change. But yeah, I honestly think that's something that we have to answer in the future.
I'll ask a second question if there's time later. Yeah, last question.
I think also commenting to your point, I think for the Forge in Fire runs, that you see a much more like toroidal dominant magnetic field, and that's a bit also different because those are lower halo mass range, and these are trying to mimic the center of the cluster, like more massive cluster elliptical. So I think that's also pretty different, the different magnetic field shape and also different environment.
I was also wondering if I can jump in here since I have the microphone, whether it matters whether the gas has rotation, right? Because then isn't the MRI very important in the Forged in Fire configuration? And here there's no rotation.
No,
right?
there's no rotation in this case.